Imagine a world where the agonizing wait for an organ transplant is a thing of the past. A world where a patient in need of a new heart, liver, or kidney doesn't have to hope for a tragedy to befall someone else, but can instead receive a perfect, custom-built replacement grown from their very own cells. Now, imagine that the factory where these organs are made isn't on Earth, but is orbiting 400 kilometers above our heads in the silence of space. This isn't a scene from a futuristic movie. This is the very real future of medicine that is being built right now aboard the International Space Station. Welcome to G Fun Facts Online. Today we're exploring how microgravity is becoming the key to solving one of healthcare's biggest challenges: biomanufacturing human organs. On Earth today, the need for transplantable organs far outstrips the supply. In the United States alone, over 100,000 people are on the national transplant waiting list. Every 10 minutes, another name is added. Tragically, about 17 people die each day while waiting for a match. For those lucky enough to receive a transplant, the journey isn't over. They face a lifetime of powerful immunosuppressant drugs to prevent their body from rejecting the foreign organ. Drugs that come with their own serious side effects, increasing the risk of infection and other illnesses. For decades, scientists have pursued a holy grail: creating lab-grown organs. The advent of 3D printing brought this dream closer. The concept, known as 3D bioprinting, is straightforward in theory. Instead of using plastic or metal, a 3D printer uses a bioink, a gel-like substance loaded with living cells, to build a biological structure layer by layer, based on a digital model. The promise is immense. Creating organs from a patient's own cells would eliminate the need for donors and the risk of immune rejection. But here on Earth, we have a fundamental problem: gravity. Living tissues are incredibly soft, delicate, and mostly made of water. When you try to 3D print them, they tend to slump and collapse under their own weight before they can mature and hold their shape. It's like trying to build a complex sculpture out of Jell-O. To get around this, researchers on Earth must use scaffolding materials to support the structure as it prints. But these scaffolds are an imperfect solution. They can interfere with the cell's ability to communicate and organize naturally, and they can sometimes cause complications or inflammation after transplantation. This is where space comes in. The unique environment of low Earth orbit, specifically the condition of sustained microgravity, changes everything. In the near weightlessness of the International Space Station, the gravitational pull is about 1/1,000,000th of what it is on Earth. That Jell-O sculpture that would collapse on your kitchen counter can be constructed with exquisite precision in space, holding its form perfectly. For bioprinting, this is a revolutionary advantage. In microgravity, soft tissues don't collapse. This means scientists can print with much softer, more biologically relevant materials. And most importantly, they can do it without the need for artificial scaffolds. They can build tissues exclusively from the bioink and the cells themselves, allowing the cells to self-organize into complex structures just as they would in the human body. This allows for a much higher fidelity of printing, enabling the creation of intricate internal architectures, like the delicate networks of blood vessels or vasculature, that are essential for any organ to survive and function. Without a blood supply, a printed tissue is just a clump of dying cells. Microgravity makes printing these vital, complex vascular networks a more achievable goal. But the benefits don't stop there. On Earth, the cells suspended in the bioink tend to settle downwards due to gravity, a process called sedimentation. This leads to an uneven distribution of cells in the final printed product. In space, sedimentation is virtually non-existent, so the cells remain perfectly suspended, leading to more uniform and consistent tissues. Furthermore, microgravity eliminates convection currents, which are tiny flows in liquid caused by temperature differences. This creates a much more stable and predictable environment for the delicate printing process. Perhaps most fascinating of all, biological research in space has shown that microgravity has a direct effect on the cells themselves. Stem cells, the undifferentiated master cells that can become any type of cell in the body, appear to grow and multiply more rapidly in space. They also demonstrate enhanced abilities to differentiate into specialized cell types. In essence, space isn't just a place where we can build tissues better. It seems to be a place where the fundamental building blocks of life itself behave in ways that are uniquely beneficial for regenerative medicine. This potential has not gone unnoticed. A new commercial ecosystem is rapidly forming in low Earth orbit, driven by companies and space agencies who see the immense value of in-space biomanufacturing. At the forefront of this movement is NASA and the ISS National Laboratory, which functions as a research hub for a host of scientific endeavors. A key commercial partner in this field is Redwire, a space infrastructure company that has made significant strides in this area. Redwire developed and operates the BioFabrication facility, or BFF, aboard the International Space Station. The BFF is a state-of-the-art 3D bioprinter designed specifically to operate in microgravity. Since its installation, it has been the site of several groundbreaking experiments. In one of its early successes, the BFF successfully printed a partial human meniscus, the complex cartilage structure in the knee. This is a tissue that is notoriously difficult to repair on Earth. More recently, and perhaps more significantly, Redwire's BFF was used to print human cardiac tissues. These patches of heart muscle were grown in space, returned to Earth, and studied by researchers. The results were astounding. The space-grown tissues showed better organization and signs of contractility. They were essentially beating. This was a monumental proof of concept, demonstrating that viable, functional human tissue could be manufactured in orbit and safely returned to Earth. The process for a future patient would be a marvel of logistics and science. It would start on Earth, where doctors would take a small biopsy, likely of fat tissue, from the patient. From this sample, they would isolate and cultivate adult stem cells. These cells would then be mixed with nutrients and growth factors to create the patient-specific bioink. This bioink would be loaded into a special cassette and launched to the International Space Station. Aboard the station, an astronaut would load the cassette into the biofabrication facility. Guided by a precise 3D model generated from the patient's medical scans, the BFF would begin its work, printing the organ layer by infinitesimal layer. Once printed, the nascent organ would be placed in a supporting device called a bioreactor. The bioreactor acts like a surrogate body, providing a constant flow of oxygen and nutrients, and sometimes gentle electrical or mechanical stimulation to encourage the cells to mature and assemble into a fully functional tissue. This maturation phase could take weeks. Finally, the finished organ would be placed in a protective container for its return journey, descending through the atmosphere in a re-entry capsule to a waiting medical team on the ground, ready for transplantation. While the ultimate goal is to print entire complex organs like kidneys and hearts, the path to get there involves crucial intermediate steps. The first commercially viable products from space are likely to be smaller tissues for research and drug testing. These lab-grown tissues, known as organoids or tissue chips, are far more accurate models of human biology than anything grown in 2D petri dishes on Earth. Pharmaceutical companies could test the safety and efficacy of new drugs on these high-fidelity, space-grown tissues, dramatically accelerating the drug development pipeline and reducing the reliance on animal testing. In the nearer term for transplantation, we can expect to see the printing of simpler avascular tissues, those that don't need an integrated blood supply, like cartilage for joint repair or skin grafts for burn victims. The technology also holds immense promise for the future of space exploration itself. For a long-duration mission to Mars, the ability to print replacement tissues would be a medical necessity. If an astronaut suffers a severe burn or a non-healing wound, a 3D bioprinter could use their own cells to print a new patch of skin for a perfect graft, millions of miles from home. Of course, the road ahead is paved with significant challenges. The technical hurdles are immense. Scaling up from a small patch of cardiac tissue to a full-sized, four-chambered human heart with its own integrated vasculature and electrical conduction system is a quantum leap in complexity. The entire process, from Earth to orbit and back, must be perfected to ensure absolute sterility and viability of the organ. Then, there is the cost. Launching anything to space is fantastically expensive, and while costs are coming down with reusable rockets, manufacturing organs in orbit will, at least initially, be an extremely costly endeavor. This brings us to the most profound challenge: the ethical and societal implications. If and when this technology matures, who will have access to it? Will a rejection-proof, custom-printed heart only be available to the ultra-wealthy? The vision of a future where the best life-saving treatments are literally manufactured off-world raises deep questions about equity and access. The scientists, companies, and government agencies pioneering this frontier have a deep responsibility to grapple with these questions now, to ensure that the benefits of this revolutionary medicine can one day be shared by all of humanity. We stand today at a remarkable crossroads, a unique intersection of regenerative medicine and astrophysics. The final frontier is no longer just a destination to be explored. It is becoming a workshop for creation, a laboratory for healing. In the quiet, sterile environment of the International Space Station, the faint hum of a 3D bioprinter is more than just the sound of a machine. It is the sound of a new dawn, not just for space travel, but for the future of human health. The dream of sending our own cells to the stars and having them return as a second chance at life is moving, with undeniable momentum, from science fiction into our reality.